Okay, we're going to take a look at example 3A on page 83 of your workbook. Okay, let's take a minute just to get a feel for what they're asking us here. So they are giving us a generating set for a vector space. Okay, so our generating set is this set G that we're looking at, and the vector space is just P2 of R, the set of all polynomials of degree 2 or less. Okay, we want to pick out a subset of G that's enough, okay, to still span P2 of R, basically. And what's interesting about this problem is we know how to solve this type of a problem if we were in Rn, the vector space of tuples. So the key here is to kind of translate this into a problem about tuples. Okay, and in this case, that's not terribly difficult to do if we just pick ourselves a nice basis for P2 of R. Let's pick the standard basis. Okay, 1x and x squared. And we're just going to reinterpret each of the polynomials in G in terms of the coordinates that it would take to build the polynomial. Okay, so let me show you what I mean. We're going to build a corresponding set that I'm going to call G prime, which is going to be the coordinate vectors for the four polynomials that we see in G. So we'll start with 1 minus 4x plus x squared and just ask how would we build it as a linear combination of 1x and x squared. Okay, well, the coefficients that we need would just be 1, negative 4, and 1. We're literally just taking the numbers in front of the 1, the x, and the x squared. Okay, we can do the same thing for each of the other three polynomials. So 2 minus 8x plus 2x squared. The coordinates that build that would look like 2, negative 8, and 2. And just keep going down the line here. Okay. So there's G prime as a subset of R3, and so the vector space that corresponds to V, which I'm going to call V prime, would just be R3. That's where these vectors in G prime live. Okay, and now here's where we go back to the technique that we developed way back in section 1.6, I believe, and ask the question, how would we pick out the vectors in this set G prime that are enough to form a basis for R3? Well, we can answer that question by making a matrix. And each column in the matrix is going to be one thing from G prime. So we'll start with 1, negative 4, and 1. Okay, and just copy each of our coordinate vectors one at a time. Okay, and we can pick out the vectors that we need to form a basis just by finding the pivot columns of this matrix. Okay, so at this point, we would do row operations. You can either do this by hand or maybe on a calculator. And I'm just going to show you the result of the row operations. So here's our reduced echelon matrix. Okay, we'd look in there and see if we can pick out the pivot columns. You can probably do that. Okay, it looks like there are 3 of them. Okay, and what we talked about before in section 1.6 says that all we really need are those 3 columns. Okay, the first one, the third one, and the fourth one. Okay, and so our basis for R3 coming from the set G prime would just look like that first, third, and fourth column. Okay, so let's write that out together. Okay, and again, that's a basis for R3 that just happens to be a subset of the set G prime from above. Okay, but what we wanted was a subset of G, the set of polynomials that forms a basis for P2 of R. So we just need to kind of think back, interpreting beta prime as being coordinate vectors, and ask, what polynomials from our original set G do those coordinates build? Okay, and since our basis was simple, that's not too difficult to figure out. 1, negative 4, 1, for example, that's going to lead us back to the polynomial 1 minus 4x plus x squared. Okay, and the other two are going to be similar. Negative 3, 14, negative 9 builds us the polynomial negative 3 plus 14x minus 9x squared, and so on. Okay, and so this last line here is our answer, and again, just to emphasize, that is a basis for P2 of R that happens to be a subset of G, which answers the question that we were asked.